We were dealing with what is known as yeah. So what was the last one that we did? What was the last result that we did? Fine. So in the last result, I think yeah. So this is the one that we did. So we defined what are known as. So we were dealing with what is known as the so-called continuity of measures. Continuity property of measures. Right. So this is what we were looking at. Fine. The first result that we saw is that if an is an increasing sequence, and if it increases to union over n in n an implies mu of an is an converges to mu of the union, right? Second, if an is a decreasing sequence, and if it decreases to with mu of ak being finite for some k in n, so this will imply that mu of an will converge to mu of the intersection, right? And then we defined two concepts what are known as lim sup and lim inf. Lim sup of a sequence is the intersection over n in n, union over k greater than or equal to n, ak. And similarly, we defined what is known as lim inf. Just defined as union over n in n, intersection over k greater than or equal to n, ak. Yes. And then two things that we had. One is that mu of the lim inf an is always less than or equal to lim inf of mu an, right? So if mu of the union is finite, then mu of lim sup an is bigger than or equal to lim sup mu an, right? Yeah. So all these we have seen the last class, right? So now it's time to finish the whole thing, right? Because we need conditions under which they are equal, right? Okay, so let me put it in the form of a corollary. As usual, let omega a mu be a measure space and let an n in n be a sequence of sets. First one, if limit n tending to infinity an exists. Yeah, in fact I forgot to tell you. Yeah, here maybe I'll put it where did right. So here let me just see. So well I'll write down what does it mean. And limit n tending to infinity mu an. If both these limit exists, then mu of the limit will be less than or equal to the limit of mu an. Yeah, this is first one. Second one, so if limit n tending to infinity an exists and if mu of the union an is finite, then limit n tending to infinity mu an is mu an exists. Mu an is finite, that means this exists, and mu of limit of an is equal to limit of mu an. Yes, right. Yeah. So maybe, so before I get into the proof, let me state a definition. Let an be a sequence of sets. We say that an converges if lim sup of an is equal to lim inf of an. So in this case, the common set will be called as the limit of an. That is the value of limit n tending to infinity an. Yes. So this common set limit n tending to lim sup n tending to infinity an or lim inf an. So if these two sets are one and the same, then you say that the sequence an converges, and this common set will be called as the limit of an. Right. So that's what is meant in these two. Right. Now let's get into the proof. Right. Right. Now here is the proof. First one. So what we wanted is mu of the limit. Right. So we'll begin with that. Mu of limit n tending to infinity a n. This is what we wanted, right? But because the limit exists, that is already given, right? It's already given that the limit exists. Therefore, this is same as its lim sup. Sorry, lim inf. I'll choose it as lim inf. Doesn't matter. Sorry. Yeah, so mu of the lim inf a n, right? But then lim inf is always less than or equal to mu of lim inf is less than or equal to lim inf of mu n. Mu a n, right? That we have used. And again, it is also given that limit of mu a n exists. Therefore, this is same as its limit. That's it. Fine. So natural question is why can't we use the lim sup? For lim sup we need the other condition. Yeah, for lim sup we need the other condition, and that is not given. Therefore, at most that you can exist, even if the limit exists, both the side limit exists, the only thing that you can expect is only less than or equal to. Right. Second one. Yeah, just give me a minute. Right, second one. Right, so what we wanted is about limit. Fine. Yeah, so we'll start with, so in this case what is happening, you can notice that limit exists, right? So and not only that the limit exists, then this is also finite. So first thing that we wanted is this limit of mu a n, this is finite. So that's what we wanted. What if you have a sequence of scalars, then lim inf is always less than or equal to lim sup, right? So to show that the limit exists, it is enough if we can show that lim sup is less than or equal to lim inf, right? So we'll begin with that. So we'll start with lim sup. But then what do we know about this one, lim sup? Yeah, that we have written here. Lim sup of mu a n is less than or equal to mu of lim sup, provided the measure of the union is finite. Yes, but that is already given here. Measure of the union is finite, and therefore this is less than or equal to measure of lim sup a n, right? On the other hand, it is also given that limit n tending to infinity a n exists, and therefore this is same as measure of the limit, which is again same as measure of lim inf. Right, but now mu of lim inf is less than or equal to lim inf of mu n. Right, that's what we wanted. So therefore lim sup mu a n is equal to lim inf mu a n, that is this limit exists, right? So we have shown one part. right? On the other hand, so by 1, what is that we know? So we have already seen, so by 1, now we wanted, so limit tending to infinity mu of an, right? An, which is equal to, yeah, so in fact, so once you know this, then yes, so there, now by 1, I'll simply say this one, by 1, it follows that only that much is expected. That limit n tending to infinity mu an is equal to mu of the limit a. That's it. Right? It's a consequence of 1. We have already shown that it is less than or equal to. Now, we have also assumed that, what is that? We have also assumed that this is finite. Which one? Yeah, this mu is finite. Therefore, we can use the other way inequality and prove things. Right? So, I'll simply say by 1 it follows. Right? Right. So, with this, the continuity property is over. Right. Now, let's get into the next topic. What is known as completion of measure spaces. Right. So let's look at a simple example. As usual, we have been taking motivation from what is known as the so-called Lebesgue measurable sets. Right. Yeah. So consider this measure. What is that? R, M. Yeah. The usual Lebesgue measure space. Right. M is the space of Lebesgue measurable sets and M is the Lebesgue measure. Right. So suppose that E belongs to M and F is contained in M with M of F equal to 0. Yes. Now what can you say about F? Any comments about F? Any comments about F? Any comments about F? In fact, we have seen this in the beginning itself. Is it a Lebesgue? Huh?
Subset of M.
It belongs to M. Yes. So this will imply that f belongs to M. Right. Right. So it is going to be a Lebesgue measurable set. This we have seen. In fact, any set of measure 0 is a Lebesgue measurable set. That much is known to us. There is nothing special about this F. So what does it tell us? It tells us that if you have a Lebesgue measurable set and a subset having 0 measure, then such a set is also Lebesgue measurable. Right.
But sir, you have already written that f is measurable in the first line.
Oh, sorry. F contained in E. Sorry. F contained in E. I'm very sorry. It should be F contained in E. That's very important. Correct. Fine. So based on this, we'll say a definition. Here is a definition. Let omega A mu be a measure space we say that mu is a complete measure on omega comma A if for every E in A with mu of E equal to 0, F contained in E implies this F should also belong to E. Yes. So if I have a set of 0 measure, then all its subsets should also be measurable. That is the whole point. Right? That is what is meant by completion. Right. So in this case, so we'll call this triplet omega A mu to be.
लो सर ये न्यू
हाँ.
सर न्यू E0 है न्यू F0 है इसमें.
How do you know that mu F makes sense? F need not be a part of A in general. How do you know that all subsets are also there? Is that clear? So this is what is known as a complete measure space. Right. So let's look at some examples. Okay, so as usual, the first one is R, M, M. R with the Lebesgue measurable sets and the Lebesgue measure. So this is an example for a complete measure space. Right. Second one, so we need one example where this is not true. Right. So you look at omega to be ABC and then the sigma algebra to be MT B BC omega. Right. So you can, okay, so I'll simply you can easily verify that A is a sigma algebra. Right. And then you define mu from A to 0 comma infinity. Well, it's not. Well, this is going to be in fact a probability measure. You don't need up to infinity 0 comma 1 as well. I have only 4 sets, so let me define it as mu of phi equal to mu of BC equal to 1. Sorry, I want it to be 0. Sorry. Yeah. And then the remaining mu of singleton B equal to mu of omega equal to 1. Yes. Again, you can verify that mu is a measure.
Sir,
Ha!
so according to the definition of algebra, sir, complement should belong to the set, then sir,
Thank
the
you.
complete.
This should be A. Sorry. Thank you.
Yes.
This should be A. That's what I've been looking at. Thank you. Yeah. Yes. This should be A. Thank you. Great. So this is a measure. Fine. And this is a sigma algebra. All these you can verify. So is it complete? Is mu complete? Is mu complete?
No, sir.
Why?
Because measure of subset B C is 0, but its subsets B and C singletons are not there.
Exactly. So note that measure of BC, this set, this is 0 and singleton B, singleton C, both are contained in this BC, but both singleton B and singleton C does not belong to script E, does not belong to the sigma algebra. That's it. Therefore, this omega A mu is not a complete measure space. Yes, so third one, let omega be any set. You choose it as any set and let script A be the trivial one, MT and omega. And then define, well, let mu be the zero measure instead of writing it as. Let mu be the zero measure. That means what? Mu of MT is 0, mu of omega is also 0. It's just the zero measure. Is it a complete measure space?
Yes, sir.
If sigma, if this set is not singleton one, then it is not complete.
So it's singleton is the given set. Then you cannot expect it to be complete. So then So you can just notice that mu is complete if and only if omega is a singleton. That's it. Done. Right. So now let omega A mu be a measure space which is not complete. See, if you have a metric space which is not complete, then you can complete it. So similarly, can you find a measure space? So given a non-complete measure space, given a measure space which is not complete, can you extend it to a completion, or can you extend it to a complete measure space? So first question is, what do you mean by extend? In what sense? So let me put it in the form of a question that does there exist a measure space A dash mu dash such that A is contained in A dash, mu dash restricted to A is mu, and this triplet omega A dash mu dash is complete. Does there exist one or not? Yeah, so yes, the answer is yes. So how to construct? Right. So here is the way to construction. This is one such, and we'll see that it is the smallest. Whatever we are constructing, it is the smallest in some sense. That we'll see. Right. So let's begin the answer to this. So let's start with what we wanted. So let me choose all the null sets invariably. So that's exactly what we started with. Yes. So we were looking at all subsets. Well, see. So here, let's look at. So we wanted all subsets of null sets. That is, those sets having measure 0. Right. So let me call script n as all those f subset of omega such that there exists B in A with F contained in B and mu B is 0. Right. Fine. So you already have a measure space omega A mu, and which is not complete, and now you have chosen this one. Right. So now, having collected all the null sets, now let me go for A tilde. Yes, it is going to be A union F so A union F such that A belongs to the script A and F belongs to script n. Right. Yes, so the first claim is that This collection A tilde is a sigma algebra. Right. Right. So first observation. What is that? So the definition of A tilde, it is a consequence of how you define this A tilde. A tilde tells us that A is contained in A tilde and N is also contained in A tilde. Yes. How? How does it follow? How does this one follow from the definition?
From the way we constructed it, like A tilde is the union of all the sets from this capital A and capital N.
So given, say, let's say A is A, how do you show that it is in A tilde?
I belongs to both friendship friendship. But sometimes we can to be fine and let A vary, and then similarly we can do for the other case.
No, we couldn't hear you. Sorry. Shami, please.
So like we know both phi belongs to both script A and script N.
Exactly right. First thing to be observed is that empty set belongs to both. That's the first thing that is to be observed, and as a result, once you know that empty set belongs to both, then everything follows. Choose A union empty and empty union F. And that tells you that A is contained in A tilde and script N is also contained in A tilde. Right. So in particular, both omega and MT belongs to A tilde. Yes. So both are in A tilde. Right. Yes. So one thing we are done. Right. Next thing. Next. So next thing that we wanted is, yes, what is that we wanted? We wanted now. We'll have to show it is closed under complements. Right. So let E belong to A tilde. So we will have to claim that E tilde belongs to A tilde. Right. So once you know that E belongs to A tilde, then there exists A in A and F in N such that this E can be written as A union F. That is by the definition. Right. Fine. Now F belongs to N. So since F belongs to N, there exists B in A with F contained in B and mu of B is 0. Right. Now you can notice that F contained in B implies B complement is contained in F complement. Therefore, F complement, what is F complement? Which is B complement union with F complement minus B complement, right? Which is same as B complement union with, which can also be written as F complement intersection with B. Right. So now, what can you say about this set?
This belongs to A tilde.
This belongs to,
This
how,
belong.
how will this belong to tilde?
Yes, sir. Uh, because B complement belongs to A
Mm-hmm.
and F complement intersection B is contained in B, so it belongs to N.
Correct. So this whole thing is in A tilde. Right. Right. Well, that is not the main thing. Fine. Fine. So we have something. Therefore, E complement, what is E? A union F whole complement, which is A complement intersection with F complement, which is same as A complement intersection with B complement union F complement intersection with B, which can also be written as A complement intersection B complement union with A complement intersection with F complement intersection B. Yes. The first set A complement. A is a set from the sigma algebra, given sigma algebra A, and B it's again a set from the sigma algebra A. Therefore, both A complement and B complement they both belong to the sigma algebra A, and hence the intersection. Now, B is a set from the sigma algebra A and its measure is 0. Therefore, all its subsets are all going to be inside the scripted and this set. Well, I'll write one more step. Union with A complement intersection F complement intersection with B. Yes, so this is a set A complement intersection with F complement intersection with B. This is a subset of B and B has got measure 0. Therefore, this set, this whole thing belongs to script n. So I've written it as a union of union of two sets with the first set from A and the second set from script n. Therefore, this belongs to A tilde. That's it. Fine. So you don't need that. The first one you don't need anything. Yes. Fine. Right. Now, second thing is about. So yeah, I don't want to. Yeah, it's not a big deal, but still I don't want to proceed today. Or let me just try to finish it. I'll just take 5 more minutes and then I'll finish. I don't have much time, but still. The next one will have to show that it is closed under countable union. Right. Let En n in n subset of A tilde. Right. Then for each n in n there exists An in script A and Fn in n such that En is of the form An union Fn. Now note that union over n in n, En is equal to union over n in n, An union Fn, which can be written as union over n in n, An union with union over n in n, Fn. Right. Now, right. So this much we have. So now, since Fn belongs to n, there exists Bn in A such that mu of Bn is 0 and Fn is contained in Bn. Now, mu of the union by subadditivity, this is less than or equal to summation over n in n mu Bn, and each one of them is 0, therefore this is 0. And union over n in n Fn, each Fn is contained in Bn, therefore this is contained in union over n in n Bn. So these two together imply that union over n in n Fn belongs to script n. Right. Yes. Therefore, union over n in n En, which is union over n in n An, union with union over n in n Fn. Now, each of these Ans, they all come from the sigma algebra, therefore this union is also from the sigma algebra A, and just now we showed that this union over n in n Fn, it is in script n, therefore this union belongs to A tilde. Yes, that's it. We have shown that it's a sigma algebra, right? Yeah. So I'll stop here for today's one. Tomorrow we'll see how to define a measure, and then we'll also see that it is the smallest. That is on not tomorrow but on Tuesday. Fine. So I'll stop here. Thank you all.